So we're going to start our final topic for the course, and a very important one, and that is graphs. So a graph is a data structure, or that's actually somewhat incorrect. It is the right thing to say, it is a combinatorial object. A combinatorial object representing what I'll say entities, and these are often called vertices or nodes, and relationships, which are often called edges. So the way to think of it is, I'm going to draw a picture. So you could have a bunch of nodes or vertices labeled 1, 2, 3, 4, 5. And then you have these edges between them. You shouldn't think of this as being represented in the plane. This is just an abstract representation of this graph. Okay, so you may have something like this. And the graph G, formally speaking, is a pair V comma E. V is a set of vertices. In our case, often we'll just think of the set just to be the first n natural numbers, just to give it a label. And E is a set of pairs of vertices. Now, if E is unordered, this is called an undirected graph. If E is ordered, this is called a directed graph. So the idea is, this is an undirected graph as drawn here, but a directed graph would actually, you can think of it as the edges are arrows. All right, so undirected. Another way to think of this is just saying that if the edge UV is in E, if and only if VU is in E. Okay, that's what an undirected graph is. And often we also have a notion of weight, that is, edges may have weights associated with them. And so you can think of, if you were representing a road network, then your vertices would be your intersections, the edges would be the roads. In some cases they're directed, in some cases they're not. Like, you could have some one-way streets and you could have some that are not one-way. And you may have a weight which might actually be the distance that road represents. So this is like a representation of a road network. And we will construct a data structure to represent that in algorithms to process graphs. And one of the most common setting of graphs that we'll be looking at are what are called simple graphs. So these are unweighted, undirected, and no self loops. So sometimes you could imagine that you could have an edge that goes from one to itself. This is called a self loop. You could imagine that there are multiple edges. These are called multiple edges between the same pair of vertices. These are called parallel edges. And these are, of course, directed edges. So in a simple graph, you don't have parallel edges, you don't have weights, you don't have self loops, and you don't have direction. So it's sort of the simplest, most basic form of a graph. And to give you an example, Facebook would represent its friend network as a simple graph, because in some sense, you're not friends with yourself. When you're friends with someone, then that person is friends with you. And it's only one relationship. There's no parallel relationship. On the other hand, if they were to represent, let's say, some kind of message like, or you could, now on Twitter, if you look at followers and followees, that's a directed network, right? Because if you follow someone, that doesn't mean that person follows you. And you can have more complex networks where you can think of chat networks or communication networks where there are parallel edges. They could be one edge for every single communication that has been made. And in that case, there will be parallel edges. You could think of email networks where people send email. Sometimes they send themselves an email as a reminder. And so that would be a self loop. So in this way, lots and lots of modern data is really represented as a graph. And in some sense, the study of graphs, which has been going on since the the earliest sort of result in graph theory was by Euler, which is like maybe, mid 1800s. In sort of in the 50s and 60s, the study of graph theory picked up, and over the past 2 decades, it's just exploded because of the significance of the study of graphs in so many things that we do these days, especially social networks. So in some sense, the study of large social networks, their prevalence, and the study of things like the internet graph, the internet network, fact that we have computer networks, distributed networks, and all of this has now led to this explosive growth in the science of graphs. And what I'll be discussing over the next few lectures are some of the algorithmic foundations on how to process graphs. And this is it's a very active area of research. So let's start with looking at our simple graphs. So I'll look at simple graphs.
Excuse me, Sesh.
Yes.
Can I see the bottom of that last page again? Thank you.
I was wondering, does combinatorial object have a specific definition?
A combinatorial object is essentially something that is represented as a collection of subsets of a universe. It's usually something that that requires. It's like something describable in a discrete context, not through continuous objects or continuous functions. So,
okay.
Yeah, so it's basically, think of it, they're also referred to as set systems. Set systems are one kind of combinatorial object.
What is?
Set systems, like
a
family, a family of subsets of some universe. So you can really think of the simplest, a graph is like a family of subsets of size 2. And there are things called hypergraphs, which are families of larger subsets. But you could also assume that maybe some of these subsets have weights or colors or various different things. And if you add these things on, you get a more complex combinatorial object.
Okay, thank you.
Yeah. So I want to look at simple graphs. Let's focus our attention on that. And so V is a vertex. N of V we'll use to denote the neighborhood of V. So what is the neighborhood? This is just a set of U. It's just that UV is in E. All the neighbors. Okay, so for example, if I were to draw this graph here, the neighborhood of the vertex 2 is 1, 3, 4, 5. The neighborhood of 1 is 2 and 3, so on and so forth. Right? You can write all the neighborhoods. In a directed graph, if you have direction, then you have out neighborhoods. And then you have in neighborhoods. The out neighborhoods are often denoted as n plus or n minus. In mathematical text, you'll sometimes, instead of n, you'll also see capital gamma. We'll just use n, and either of these is sort of common in the literature. One of the issues with graph theory is that off late it's been co-opted, or it's been used by many different disciplines, and they all come up with their own notation, which can be kind of annoying. So I will kind of stick to notation which is, from graph theory and math, which is sort of what theoretical computer scientists or most computer scientists would use. So when you have a directed graph, you have edges that are coming in, and you have edges that are going out. So that which is coming in is the in neighborhood. That which is going out is the out neighborhood. Now, we will not be talking too much about direction, but it will be something that will come up a little further in our lectures. An important notion is the degree of vertex V. So the degree, this is just the size of the neighborhood. This is the number of neighbors, the number of distinct neighbors. And similarly, what you could have here is an in degree and an out degree. Okay? So in degree and an out degree. So let's begin. Okay, so any questions about what a graph is? We now need to talk about how to represent it, but do you understand sort of abstractly what a graph represents? Indeed, sorry, go ahead. Question?
Yeah, sorry, my mic was cutting out. Looks like just clarifying here, in neighborhood is with the superscript minus?
Yes.
Okay, and then on the previous page, you mentioned if E is ordered. Are we talking about sorted or like ordered pairs?
Ordered pairs.
So its elements are all ordered pairs?
Meaning that you're looking at the set of pairs where you actually care about the ordering. That's basically saying, like, you think of UV as being distinct from VU. Right? When you look at sets, you can look at ordered sets and unordered sets.
Yeah, I'm following that much. I was just kind of throwing it.
Yeah.
Sense of.
Yeah. Okay. So now the question is how to represent a graph. Now, unlike the other data structures, where really you think of the data structure as storing some sort of evolving set, right? Like if you think of a binary search tree, think of inserts and deletes being really important and finding and things like that. In a graph, it's not just the evolution that's important, but rather how do you process a fixed graph? So if you look at, graphs change over time, but we also wish to process fixed graphs. So maybe the way to explain this is if you think about Google Maps and the fact that it's solving things in the road network. And that's actually what they do. They store all the roads as a graph. And when you say I want to go from here to here, they're actually looking through the graph. The road network doesn't change that often. So the fact is it's not changing too much over time, but you're trying to process that fixed graph over and over again. On the other hand, there are some graphs that change much more rapidly over time, like a tweet network or a follower network in Twitter will often have these bursts of activity. And a lot of these considerations affect how you store the graph. So how to store a graph is actually like an active research area. It depends on your application. But what I'm going to talk about are some of the basic methods in which you would want to store a graph. So let's start by maybe the most simplest and seemingly the most obvious and almost like, stupidest method to store a graph. But you'd be surprised that actually in many cases this is what is used in industry. It's just a list of edges. And they use it in industry not because they don't know any better, it's actually because for many situations, the simplest data structure is actually the best that works in practice. Just maintain a list of edges. So you just have an array or a list or linked list or whatever have you, just a list of pairs. So you'll have U1 V1, U2 V2, U3 V3, so on and so forth, UK VK. Right? Just a list of edges. Simple, easy. Now what we're going to talk about is to try to understand how big these representations are. So let n is usually the number of vertices, and this is extremely common when one talks about graphs and algorithms, which is to have n and m and the number of edges. So the storage size for this is also sometimes called a raw list of edges. Storage size for a list of edges is simply, it's just m, or O of m, depending on whether you have a linked list or how you want to store things. It's essentially just O of m, which is the best you could hope for. The storage size is simply the number of edges that are there. Okay. Now let's look at a more fancier method to store things, which you may have heard, which is the adjacency matrix. So what is the adjacency matrix? The way to think of it is basically it's a matrix where it's a matrix M where M U V is 1, or sometimes this is also called A, the adjacency matrix A is 1 if UV is an edge, 0 otherwise, and so A is an n cross n matrix and if A transpose is equal to A, then the graph is directed. Graph is undirected. Right? Because then that would mean that AUV is the same as AVU. It's easy to store weights. Like instead of this, you could also store the weight. This could be the weight of the edge UV. Okay. So this is the adjacency matrix. And now here is the question: how much storage does the adjacency matrix use? Is it basically O of n? We'll just say theta. Is it O of m or theta of m, or is it theta of n squared? So I'm polling you. So there is some confusion, but it's theta of n squared, and that's because you have to store the entire matrix. You're storing n times n. It's an n cross n matrix, so there are n squared entries in there. Now, an adjacency matrix, when you initially look at it, seems very appealing. It's a very clean way of storing a graph. It seems very easy to insert, look up an edge. Like if you think about you having a list of pairs and you want to look up, is U a neighbor of V? You're going to have to go through that entire list. In an adjacency matrix, you just have to look up one entry in the matrix. So adjacency matrices are very good for looking up whether an edge is present or not. On the other hand, the storage is just humongous. Let me try to convince you why this would be unsuitable for today's purposes. Let's think of a social network like Facebook, just as a rough approximation, let's look at maybe the size of the social network within the US. Like they probably store things by geographical area. So let's say you've got 100 million vertices. How many edges do you think that's going to have? So this is 10 to the 8. Any estimates on how many edges do you think? This is let's just say this is the social network within the United States. Okay, so about 100 million people. Rough approximation. How many edges are there going to be? Any thoughts?
Maybe 10 to the 10 through 10 to the 11.
10 to the 10 to 10 to the 11. So it's just saying every person has maybe about 100 or 1,000. I don't even know. They probably cap things, but yeah. So that's a reasonable estimate that the number of edges is about 100 times that. So it's about 10 to the 10. Let's look at how much storage an adjacency matrix uses versus how much storage a raw list of edges would use. Okay. So the adjacency matrix, I'll put this right here. And I'm just using very rough approximation so that you see this. That's about 10 to the 8 squared bits. That's 10 to the 16 bits. Okay? Approximating, I'll say that's 10 to the 15 bytes. Okay? 10 to the 15 bytes. Right? So 10 to the 3 is kilo, 10 to the 6 is mega, 10 to the 9 is giga, 10 to the 12 would be a terabyte, and 10 to the 15, that's 1 petabyte. This is 1,000 terabytes. That's 1 petabyte.
Can you repeat the word? What is it? Petabyte? Terabyte?
PETA, petabyte, and this is a terabyte. So your hard disk is, maybe you might have a 1 terabyte hard disk. 1,000 of those. So trust me, an industrial strength distributed system, the kinds of things that Facebook and Twitter can own, will not have 1 petabyte of storage. When you actually want to process the graph. Of course, they have petabytes of storage, but that's a lot. That's 1,000 computers. Because even a big computer is basically just composed of small little computers, right? Like a big distributed system. This is immense. This is huge. There is no way that you could process this sort. You can store it, you can process it, but it's going to be very inefficient. Instead, let's look at the raw list of edges. Okay, the raw list of edges, that's essentially just going to store 10 to the 10 edges. Each edge, you could think of as storing something like 2 longs, right? So maybe, it's about 20 times 10 to the 10 bytes, 20 bytes to maybe store each edge. Okay? So this is 2 times 10 to the 11 bytes. That's about 200 gigabytes. That you could probably, depending on when you got your laptop or your computer, you could probably fit into your hard disk in one machine. Right? So the difference is needing industrial strength storage, huge amount of storage for an adjacency matrix, versus something that's actually very manageable even on your own computer. And this is for storing like the entire social network of the United States, which is a huge object. It's a huge object, but you're able to store this reasonably on your own machine, or on a slightly more, like a buy a machine for 2-3K, a good server, and you can easily store this. Okay, and that's one of the reasons why you might a raw list of edges beats an adjacency matrix. Okay, any questions about that? Yeah, go ahead.
Yeah, so I was just wondering, is there a way to combine the raw list and the raw list of edges and then the adjacency matrix?
Yeah, it's a good question.
Can we use for example, can we use the vertices as index?
So good question. So
access?
yeah, so for better access, what you can get is you can try to combine the benefits of both using something called an adjacency list. It doesn't give you all the benefits of the adjacency matrix, but it kind of indexes things in a better way. But even then, sometimes having a raw list of edges is actually useful. But you'll see that for many of the algorithms, it becomes complicated. And this is exactly leading off to the next point on using an adjacency list. So what is an adjacency list? And you see this is going to look a lot like a hash table with chaining. It's an array of linked lists. It's an array of linked lists. Each neighborhood is stored as a linked list. So if we think of the vertices just being the first n natural numbers, so this is vertex 1, 2 up to n, and what you have is you just have a linked list that stores each neighborhood. Okay? Now the storage here, it's not it's really theta of m plus n. And the reason you have a plus over there, it's exactly the same argument we use for chaining, that you need to store a head pointer for each of these. So if m is like n squared, what that means is if most pairs are connected to each other, and this is called a dense graph, well then the storage is basically theta of n squared, right? Because if m is like n squared, then each of these is like a huge long list, which is pretty much the same as an adjacency matrix. Meaning if your graph is dense, then an adjacency matrix is what you should use. But often in most applications, there are applications where graphs are dense, but in a lot of modern applications, especially the kinds of things you do with social networks, m is usually much, much smaller than n squared. And you saw an example over here where n squared is 10 to the 16 and m is 10 to the 10. So there's a gap of 1,000,000 between m and n squared. And so when m is much smaller, m is close to n, the graph is often called sparse. When m is like O of n. So m you can think of as m is roughly the same as n. The graph is called sparse.
So you're saying that a dense graph is where each node has connections to most of the other nodes?
Exactly.
Sparse would have just a few connections?
Exactly. So you can think of the way to think of it is the average number of connections in a dense graph is like theta of n. It's like a vertex is almost connected to a constant fraction of everything else. In a sparse graph, a vertex is only connected to a constant many things, which is what a social network looks like, because you don't know most of the people in the world. Most people would have degrees of about 10 or 100 or 1,000. There are instances where one looks at dense graphs, but those are different applications.
Okay, thank you.
Okay, so now that we have these three representations, the raw list of edges, the adjacency list, and the adjacency matrix, I want to draw out this table to basically show you, draw this out. This page, when we've done this where we have different representations, we have different data structures and different operations, and we get this matrix where we put running times in each of them. I'd like to do the same thing over here. So we have a raw list of edges. Then we have the adjacency matrix. And then we have an adjacency list. And by the way, you shouldn't think that social networks are the only application of graphs. I mean, the reason I use social networks is because they're familiar enough to all of us, and it's more to you than to me, frankly, that you can connect the concepts that we're talking about here to things in your everyday life. But graphs come up in like all kinds of applications beyond, in all kinds of scientific applications, in all kinds of places. Graphs and graph theory are like, one of the most important algorithmic directions in sort of modern society. So one of the things that you may want to query, so this is the data structure, and this is the query. Is UV an edge? Right, which makes a lot of sense. The other one is to get all of NB, is to get the entire neighborhood. So let's say you want to see the entire neighborhood. Then you might want to do an insert edge. And you want to delete an edge. So in the raw list of edges, if you want to look up an edge, you basically just have to traverse the entire list. In the adjacency matrix, this is actually very efficient. That's one of the benefits of having an adjacency matrix. The adjacency list gives something in between. So I'm going to parameterize it differently. I'm going to say it's O of theta of dv, where this is the degree. So what I mean is it's the length of the list. So you just have to look at all of its neighbors. You don't have to look at all the edges. This is a huge difference in practice, right? Whether you have to look at all the edges or you just look at all the neighbors. To get all neighbors, again, this is theta of m, which is a hassle. And let's just say the delete edge with a pointer. To get all of NV here, so this is theta of n, because you have to look up the entire row of that matrix or the column. The adjacency list is the best over here. And indeed, this is one of the most important operations, as we'll see, to get all of your neighbors. Because if you think about what happens in a graph, there is a crawl. Like you're looking at a vertex, you want to look at all the neighbors. If you've ever heard of like a crawler on the web, that's what it does. It starts from a website and looks at all the neighboring websites. The fact that you can get all of the neighborhood is the important operation. The great thing about a raw list of edges is that inserting is cheap. But inserting here is also pretty cheap. And inserting here is also not that bad. Like you just have to insert in it. So the insert is actually pretty simple in all of them, although it's the easiest in the raw list of edges. If you want to delete an edge, given a pointer, then you can do that in theta of 1 in the raw list, just by saying that if it's a linked list, you can just delete. If it's an array, you can swap with the end, and you can get rid of it. Adjacency matrix, of course, these are really easy. And the adjacency list, again, once you get the pointer, once you've done this work, this becomes easy. I want to sort of break these operations up into two different ways. These are sort of change operations. And these are what are called traversal or explore operations. Now, unlike most data structures that we've studied so far, where the change is really important, so there's a change and there's a lookup, and we care about both of them. In graphs, often, depending on your situation, the change is not as important as the traversal, depending on your application. But in many applications, the traversal is important. The fact that you can get to the neighborhood is really important. Any questions at this point? Because now, after, this is going to sort of close our first subchapter of this lecture, and we move on to a next subchapter. So I'll take any questions you have about these things now.
Is this only in the case for simple graphs, or is it the same for both?
It's pretty much the same for both. I mean, I guess if you have a weighted graph, then you will typically just store the weight along. You'll have an object which stores the weight as well as the edge. And if you have direction also, it doesn't change things all that much. There are some technicalities, as in a directed graph, is the adjacency list going to store only the out neighbors, or does it also store the in neighbors? Right, so there are these things where you could double the amount of memory. You store the in neighbors and the out neighbors separately, and then traversal becomes easier. Or if you're memory constrained, you will only store the out neighbors, which is actually enough to do many things, but then looking up the in neighbors becomes expensive. So there are lots of trade-offs in this. And indeed, there are some operations where the raw list of edges is really easy. And a simple one is, let's say I have two graphs on the same set of vertices and I want to combine them. Then, the raw list of edges is really easy because you could just stick it together. Or let's say I have a graph and I want to split it into a bunch of parts and send them each to a separate processor. The raw list of edges is great because it's easy to split up an array. To divide up an adjacency matrix or an adjacency list in even portions is really difficult. So what often happens is in a lot of distributed algorithms, they'll actually be storing the graph as a raw list of edges because it's easier to process it that way. So this is, it's sort of a huge and complicated area on how to store a graph, but this is sort of giving you just the basics of what you can expect.
Great, thank you.
Any further questions?
Just to clarify one more time, the degree is just kind of the number of edges that something has.
Exactly. So
right.
Exactly. The technical term used for that is that it is the number of edges incident to a vertex. I'll maybe just write that down because that's sort of the mathematical term that is used is it's the number of neighbors, which is the same as the number of edges incident to V. It's sort of like incident means like touching V, right? So the degree of 2 in this case is 4. The degree of 1 is 2. The degree of 3 is 3. The degree of vertex 4 is 2. The degree of vertex 5 is 1. I should have also added that you can also have a vertex like this, and this is called an isolated vertex. This is called an isolated vertex.
Okay, thank you.
For the isolated vertex, would you just represent the edge for that as like mapping to itself or something, or
there would be no edge. So what you can think of is in the adjacency matrix, it would just have just that linked list would be null. Like the neighborhood is the empty set.
Okay, got it.
So you wouldn't put a self loop.
Right, that would be a self loop.
That would be a self loop. A self loop denotes a distinct sort of distinct object than an isolated vertex.
Okay, got it. Thanks.
I had a quick question.
Mm-hmm.
Is a sparse graph kind of like a sparse matrix?
They're the same thing.
Okay.
Yeah. So sparse matrices and sparse graphs are the same. Actually, because you asked that question, If any of you have used MATLAB and you know that MATLAB has a different sparse representation for sparse matrices and dense matrices, sparse matrices are represented as adjacency lists. And you can kind of convert that to a dense matrix format, and then certain operations become faster. So there is a very close and intimate connection between matrices and graphs, because again, just showing you the adjacency matrix. So actually you can represent a matrix as a graph and a graph as a matrix. And a lot of matrix theory applies to graphs and a lot of graph theory applies to matrices.
So this is exactly the same way that you would set up, say, a 3D model for a rendering program, right?
You mean
Yeah, if you wanted to make a 3D model for rendering in like a 3D rendering program.
Yeah, you would. Well, sometimes it depends. Like in some cases, if you're just going to store all the pixels, then you don't necessarily need a graph. Then
well, that would be a rasterized version of it.
Right.
If
yes.
you're keeping everything in 3D spaces, then you would represent it like this, right?
Yes. Yes, that is true. Yes.
What was it you said about it was the adjacency list, that when it's sparse, the performance is good, but if it's dense, it's poor?
Yeah. So it's not a question of it being poor specifically. It's just that if it's dense, then the storage of an adjacency list is the same as the storage of an adjacency matrix. So usually when the graph is dense, you might as well store it as an adjacency matrix, because the conveniences of the matrix, you get the conveniences of the matrix, and you get the running times are going to be all the same, because in that case D of V is essentially n. And the benefit of the adjacency matrix is that edge lookups are really cheap. When the graph is sparse, then you want to store it as an adjacency list, because the storage is much smaller, and then a lot of operations will become faster. A lot of traversal operations.
Excellent, thank you.
Is degree of V big O of n squared?
I'm sorry?
The function degree of V, is that essentially big O of n squared?
Big O of n. Because the degree is at most the number of neighbors, and the number of vertices. N squared is the number of edges, but that's like the sum of all degrees.
Sure. Okay.
Yeah.
Gotcha.
But yeah, I should write that. So, D of V is essentially O of n, but it can be much smaller. But it's always at most n. It's always at most n. All right. So with sort of this preamble, now that we have this notion of a graph in place, now let's talk about graph algorithms, and let me tell you about arguably the most important graph algorithm, which is called BFS. It's breadth first search. Technically, BFS is, I'll say, just a method to traverse a graph. And so traverse is basically a fancy word for visit all vertices and edges. So it's just a method of exploring the graph, but it's really a technique to solve many problems. So there are many different problems where essentially the solution is to take BFS and maybe tweak it in some way. And BFS fundamentally works with the adjacency list. You can do it with an adjacency matrix or a list of edges, a raw list of edges, but I'm going to be talking about it assuming the graph is represented as an adjacency list, and all the runtimes that I talk about will be assuming that it's an adjacency list. So we need to get some definitions in place before I do BFS. I will caution you though that I'm going to teach BFS and hopefully it will make sense and you'll understand it. But the best way to really understand what BFS is doing is to draw an example on paper or on a board and actually run the algorithm by hand. Take a graph with about maybe at most 10 vertices so that it's not too big, and then go ahead and run BFS from a vertex. I will also give you a link to a simulation that does the same. It's good to use a simulation, but it is actually much better for you to do it by hand, do it yourself. Run the pseudocode step by step on a small graph, and then a lot of things that I'm saying about BFS will become a lot more clear. So please do this to really understand how BFS works. Take the pseudocode, draw a small graph, and run it on paper. So let's start with sort of the basics, the most stripped down version of what BFS does. For that, I need to define something called connected. So now you'll see that a lot of my writing is going to be much more mathematical, and that's because when we do graph algorithms in graph theory, we have to sort of define lots of concepts, and we use mathematical formalism to define all of that. We'll say vertex U is connected to vertex V if there exists a path of vertices from V to U. So the idea is if you have a vertex V and you've got some series of edges and that ends up at U, then you say U is connected to V. When it's directed, the notion of connectivity is more complicated, but usually what that would mean is you can get from V to U. So U is connected to V if you can get from V to U. Okay, so for simplicity, in today's lecture, let's talk about undirected graphs. So when V is connected to U, then U is connected to V, and these things are all the same. Now BFS, in its simplest version, has an argument S, and this is called the source vertex. So BFS has the basic version of BFS has a single argument, which is a source vertex. I'm assuming BFS is like a method within a graph object, so I'm not passing the graph itself as an argument. Right? I'm just assuming the graph is fixed and this is a method within a graph object. So BFS is going to output something. It outputs a tree of vertices with S at the root. Okay, what it's going to output in the end is going to be a tree, and this is a very special tree. This tree has the following properties. 1, all vertices connected to S appear in the tree. So it's going to output this tree so that all the vertices that are connected to S, so that all the vertices that S can reach with a path. So in the directed case, it's like S can reach all those vertices. So all these vertices will appear in the tree. The The second, and this is in some sense one of the most important properties, is that the tree is a shortest path tree. Okay, what do I mean by that? So let me draw a picture. So you have this tree. It's not a binary tree, it's just a tree, which means that some nodes may have lots of children, some of them might have a few children. You end up with something like this. For any v, so pick any vertex v. Maybe this is v. The path from S to V. So there is a path that goes from S to V in the tree is a shortest path from S to V in the graph. Okay, so what am I saying here? So in a graph. So now let me now start doing some more definitions. I've already used the term path. You probably understand it. But I'm just going to define a bunch of things and then I'm going to come back to visit this notion. So let's define. We'll just say a path from S to V is a sequence of edges. A sequence of edges S comma U1, U1 comma U2, U2 comma U3, so on and so forth until UK to V. It's just a sequence of edges that links S to V. Okay? The length of the path, is the number of edges in this path. So this path I gave here has a length of k plus 1. Okay? Now we'll define the shortest path distance which I will often just call distance between S and V, and this will be denoted DSV, is the length of a shortest, which is the minimum length path from S to V. So what I'm saying is, if you look at the graph S to V, you could have lots of different paths that go from S to V, and some of them might intersect each other. But amongst these paths, there happens to be this one path which is the shortest. This might not be unique. There could be multiple shortest paths. There could be a completely different way of getting there. But the shortest path distance in this setting, assuming this, is 3. BFS is going to actually give you one of those shortest paths. But even better, it's going to arrange all the paths, all the shortest paths. It will arrange a shortest path for every vertex to V. So it fixes S. S is the source. You fix the source. It's going to give you a shortest path to all the from S to all the vertices. It's going to give you the shortest path, and it's going to arrange all these shortest paths in a tree. It is a very convenient data structure. Okay? That is what BFS achieves. Are there any questions about what the output is? I'm going to tell you what BFS is achieving. I'm going to tell you how BFS achieves it. I'm sorry. I'm going to tell you how BFS does it. But right now what I want you to understand is, what is BFS doing? And it's outputting a shortest path tree. Really, this is really the thing. It's a shortest path tree. Technically, 2 subsumes 1, but I want to put both of those so that you see it. All vertices that are... Sorry, let me just finish this. All vertices connected to S appear in the tree. For every vertex V, the path from S to V in the tree is actually a shortest path in the graph. Questions? Yes, someone had...
Yeah, so I understand that, like, the tree and everything, but if it's not a binary tree, how would you find V from S?
Good question. So it's not a binary tree, and you've asked a very relevant question of how we're going to represent this tree and how we're going to search. So you shouldn't think of this as searching for a vertex. Think of it the other way around. Given a vertex, you want to search for the shortest path. So let's say you have a pointer to V. Well, then you can just go up the parents and you'll get to S.
Okay. Yeah.
So, and this crawling procedure forms the basis of so much that you actually see. And for example, how does Facebook or Twitter know what content to recommend to you? How do they know that you should be friends with this person? What they're doing is they're basically doing some kind of a crawl from you in this graph, and they look at things that are close by. You have your friends, but what about things that are close by? That's how they find things. How does Google search? How is it that when you actually put in a keyword, it outputs all these websites that are magically relevant? What Google is doing, it's much more sophisticated, but one of their core things is to do some kind of a crawl in a network. So they look at all the links of web pages, and they kind of crawl that to understand if many different paths starting from particular topics are bumping into the same vertex, then that's an important vertex, and that's how they report that to be the top. This is done in a much more complex way. Google Maps is basically doing Dijkstra, which is like a form of BFS, but it's finding shortest paths. Like, that's really simple, right? You're putting a source vertex and a destination, it's finding a path for you. And this is the simplest version of finding paths. Routing in a network, when you're doing when you are actually accessing a website, there's this whole networking protocol of TCP/IP that goes under the hood, where basically you're sending packets to some router, which sends it to another router, which sends it to another router, which is basically going to the server. All of that is basically finding paths in graphs. And BFS is like one of the most canonical basic ways of finding shortest paths. Okay? So this is very important. And I want you to understand BFS. And I repeat, it is not enough just to listen to my lecture and then go back and forget about it. You have to run BFS by hand on paper. Draw a small graph with about 10 vertices. Run the BFS pseudocode on it from every vertex. See what the output is. And then a lot of this is going to make real sense. Your fourth homework is also going to be based on BFS. And I will put that out shortly. But before that, I really want you to go and run a small example. Let me now tell you what BFS starting from a source vertex does. Now there are two fundamental data structures that it maintains. And this is how this is what it's really going to output in the end. So before I talk about the algorithm, I talk about the output. I said you saw the output as a tree, but how is this tree being stored? It's not being stored as a normal BST. I mean, it's not binary. It's not going to store all kinds of pointers. It's actually going to have a much more succinct and smaller description. So we are going to think of the vertices as numbered 1 to n. This is for convenience. In general, your vertices are not going to be labeled 1 to n, and you need to figure out what is the right data structure. I've taught you all these data structures. You can think of which of these is going to be applicable for that setting. This is the output of BFS. So the first is it's an array called predecessor. This is an array indexed by V. So you can think of it as basically an array predecessor of V. This is the parent of V in the BFS or the shortest path tree. So someone had asked the very relevant question of how are you actually going to find stuff in the graph in this tree. So what it does is it's simply going to store a pointer to the parent or an index to the parent. So it's just storing, one way to think of it is just storing parent pointers. It's not storing child pointers. So the reason is because you're just trying to go from a vertex up the tree and get to the root. Right? That's how this works. So its predecessor of V is the parent. It's the parent. So this is one array that's maintained. The second array, which is very important, is visited. This is an array indexed by V. And visited of V is basically just going to be, it's just Boolean. This is like a Boolean array. It's going to be false if in the end if BFS of S does not visit V, and it's going to be true if BFS S visits V. So these are going to be the things that are output by BFS. Now let me give you a description of the basic pseudocode of how BFS works. First, it's going to initialize Q. So Q is a first in, first out. Q is the normal queue. And sort of going back to, I don't know if anyone remembers this, questions of what are queues used for? The data structure. We've actually never really seen a queue pop up before. We've seen stacks, and we did all this stuff on stacks and recursion. What about queues? The classic use of a queue is breadth first search. So it's a FIFO queue initialized with the source vertex S. Predecessor is initialized to all null, and visited is all false. So predecessor is just going to be null, everything is null. Visited, everything is false. Now here is the key procedure. It says while the queue is not empty, it is going to perform the following operations. While the queue is not empty, U is going to be whatever is there at the head of the queue. It's going to dequeue. It's going to remove whatever is there at the top of the queue. Then it's going to say, I have visited U. So visited of U is going to be set to be true. It's going to be true. And then we have sort of our crucial loop. It says if, so I'll say while Q is not empty, if, for every vertex in the neighborhood of U, and this is traversing adjacency list. Traversing, right? It's going to loop through the adjacency list. If visited of V is false, so if it has not visited a vertex, if vertex has not been visited. And then there's sort of one more thing over here. Then it sets the predecessor of V to be U, saying that I visited V from U. Because every vertex in the neighborhood, it checks, have I visited this vertex? And if you've not visited this vertex, it's not going to immediately make it visited. It actually makes it visited over here. And then the important step is that it does enqueue of, V. So V is added to the queue. This is just saying that V is added to the queue. So what this is important is that V goes to the end of the queue. And that's why it's called breadth first search. Okay, so the way you want to sort of visualize this is, let's just say you're at a vertex U. And I'm going to color visited. I'm going to shade everything that's been visited, right? So it's got some neighbors here. Let's say these are already visited. These are already visited. Then U is visited. So it's going to shade U. Then it's going to look through all of the neighbors. It's going to say this, oh, that's been visited. This, that's already been visited. This, that has been visited. Now it's going to go there and say, okay, this has not been visited. And so this is your V. The predecessor of V is going to become U. And then V is going to go into the queue. Then it's going to go to the next neighbor. And then it's going to say, oh, the predecessor of, let's say, I'm going to call this V prime. Excuse me. So V prime has not been visited. The predecessor of V prime is going to become U. And then V prime ends up in the queue. Now, why this algorithm works is pretty non-trivial. It's tricky. But what I will do is, so let's actually, at this point, let me pause and say, are there any questions about what the code is doing? Why it works is much more trickier, and it has something to do fundamentally with the fact that this is a queue. But do you understand what it is doing? Questions?
So I guess one verification is, so even though you enqueue it only when you dequeue it from, like when you dequeue a vertex, do you actually consider it visited? Is there a reason why we do it like that? I guess I'm trying to wrap my head around that part.
I guess because what's convenient is that everything in the queue has not been visited.
Okay, got it.
Right, so you think of the queue as some sort of, okay, so you can think of, and this is a good point, there are actually three phases of a vertex. One is the vertex has just never been seen by the algorithm at all.
Right.
One is it's been seen, but it's sitting in the queue.
Mm-hmm.
And then the third is it's been visited.
Okay, so it's kind of going through that intermediate phase.
Yeah, this is an intermediate phase. So if you look at CLRS and you look at the implementation there, they give it colors. So they call it initially it's white, then it's gray, and then it's black. So and so this in this intermediate phase, it's colored gray.
Okay, got it. Thanks.
Yeah. Yes.
Yes. So I was just wondering what would be the output, because every time you dequeue, the output is not going to be the shortest distance, right?
So,
or do you store the output as the tree?
The output are these arrays. The queue is not the output. The output, these arrays form the output.
Okay, I see.
Right? So in the end, what you get is the predecessor array. So I'm going to discuss the output shortly. But the output are basically these. It's outputting these two arrays.
So those two arrays together basically would be our the BFS tree, right?
Yeah, and actually you don't even need the visited array. It's actually just the predecessor array that matters.
Because at the end of it, every node is going to be visited, right?
Every connected node is going to be visited.
Yes. Yes.
Every connected node is going to be visited. But this is actually very important. Sometimes in a graph, you want to find what are called connected components. And then what you actually do is you look at the visited array to find out what are all the things that have been visited and what has not been visited.
I see.
Does that make sense?
I also have a question.
Yeah, go ahead. Yeah.
So it's like the predecessor V is like it's not the index of V, right? It's just like the predecessor that have V in it.
So the sorry, say that again.
So like a square bracket V, like it's not describing the index, right? Because you are array.
I mean, it is the index, just as an array. It's exactly like an array, right? It's a predecessor. It's an array indexed by V. So V is a vertex, and it's telling you what is the predecessor at that position. You should just think of it as just an array of length n, and everything in that is just a number, and it's just the number is the parent of the vertex.
Oh, okay.
Does that?
Oh, just like the index is equal to the value.
The index is the vertex, exactly. The index is exactly the vertex.
Okay. Got it. Yeah.
Any other questions? Any other questions about this?
So what's at the bottom? What's getting enqueued? Is that B?
It's V. It's the neighbor that's being enqueued.
For number 3, it says for every V in N of U.
What
does N mean?
That's the neighbors, all the neighbors.
Oh, okay.
This is the adjacency list, right? So going back to this picture here, sorry. Going back to this picture here, it's going to just walk through that list. That's what the for loop does. The for loop is going to just walk through that list.
Okay, got it. Thank you.
So from here on out, like all these graph algorithms that we're talking about, we're going to be working with the adjacency list alone, or
adjacency list alone.
Okay.
Yeah. Okay, so I have, I guess, what is it? I have about 15 minutes left. So I'm just going to tell you the properties of the output of BFS, and then I think I'll maybe show you a small visualization, and that will sort of help you understand what is going on here. So I want to, and these slides that I've written, I want to use them for reference, but they're not going to explain what is going on. The way to understand it is to watch visualizations, to do it by yourself. So now that you have the pseudocode, run this pseudocode on a small graph, and things will become much more clearer. So when BFS of S terminates, the following hold. One has to prove these mathematically. I'm just sort of stating them, and then the next lecture maybe we'll discuss a little bit about how to prove these statements. First, visited of V is true if and only if V is connected to S. The predecessor of V is null if and only if V is equal to S or V is not connected to S. So you'll see that if a vertex is never seen whatsoever, then its predecessor is going to be null. But also, and this is sort of important, is that the predecessor of S is null because S doesn't have a parent. And this is going to be useful when you want to use the tree to find a shortest path. And third, and this is really where the shortest path property comes in, it's for V connected to S. The vertices V, predecessor of V, predecessor of the predecessor of V, so on and so forth, going all the way up to S. You'll see that it always goes back to S. So you take the vertex, take its predecessor, take the predecessor of the predecessor, so on and so forth. These vertices form a shortest path. Slight abuse of notation here. Technically, the edges between these form a shortest path. But hopefully that makes sense. Okay, so what this is saying is the way to think of the tree is really that you have S, and then you have various vertices. This is predecessor. I'm thinking of it as a pointer to another vertex. Remember, it's not storing the tree as you would normally store a tree. It's not creating nodes. It's implicitly storing the trees through a predecessor array, where this is just the predecessor. So if you start with V, then this is the predecessor of V. You follow the predecessor of that, follow the predecessor of that, and at some point you're going to hit S. Because you're going to keep going until you hit something whose predecessor is null, the predecessor of S is null, and this can never hit anything which is, this will not go to any other vertex. Okay, so on and so forth. So this is the way to think about the tree. Questions?
This algorithm doesn't provide duplicate routes, right? Like shortest path.
No, it provides.
It only gives you one of them because once the node is visited, they can't be revisited again.
It's a good question. So it doesn't give you multiple shortest paths. If you think about it a little bit, it can give you multiple. It will give you multiple paths, but not multiple shortest paths. And remember that, if it ever hits a vertex that's already been visited, that's actually discovering another path. It's just that that path is not stored. It's a very valid question, though. Very valid question. But it gives you one shortest path. It's a very interesting question to find many or all shortest paths, and that's actually considered a challenging problem in its own way. All right, any questions? All right, so I'm going to now show you a visualization. I'm going to put the link on the website as well. And as I said, use the visualization, but I want you to run the process by yourself on paper. I think you learn more by doing that than just a visualization, but the visualization is also helpful just to corroborate and make sure that whatever the way you're running it is correct. So I'm going to run the visualization as follows. So give me a second to sort of get all of this in order.